Hello everyone and welcome back to the series of Digital Logic Design. Today we will study how to convert a number from one number system to another. We will start from decimal to binary conversion when the number is integer or fraction. Similarly, we will perform decimal to octal conversion and cases will be integer and fraction. And then we will do binary to octal, then binary to hexadecimal, and finally octal to hexadecimal conversion. And then we will summarize number system conversion. We will study decimal to binary conversion, and at first we will perform this conversion for integers only. And for this conversion we will use successive division by base, which in this case is 2, because we are converting a number from decimal to binary number system. In every division we will take remainder as a coefficient and the quotient will be repeatedly divided. For example, we have a number 13 to the base 10 and we wish to know equivalent binary. For this, at first step we will divide by 2, we will have a quotient of 6 and remainder will be 1. The quotient 6 will be again divided by 2, now the remainder will be 0 and quotient will be 3. Now continuing successive division, 3 will be divided by 2, we will have a quotient 1 and the remainder will also be 1. So we will again use successive division, 1 will be divided by 2 and now the quotient will be 0 and the remainder will be 1. We know that in this case the remainder can be either 0 or 1. The remainder obtained from the last successive division will be act as a MSB or the most significant bit, and the remainder obtained in the first division will act as LSB or least significant bit, and we will write the remaining bits in the reverse order as they are obtained. Like in this case, A3 will be MSB, then A2, then A1 and finally A0, which is LSB. And now we will study the case of fractions, how they are converted to binary. In this case we will use successive or iterative multiplication by base. After every multiplication, the integer obtained will act as a coefficient and the fraction part will be multiplied again. Now consider example of 0.625 to the base 10 and we wish to know the equivalent binary. For this we will multiply this by 2 and we will have a number of 1.25, where the 1 will be act as a coefficient and the remaining fraction 0.25 will be multiplied by 2. Then we will have a number of 0.5. Now the coefficient will be 0 and the remaining 0.5 will be multiplied by 2. The result will be 1.0. Here 1 will act as an integer. Now we will write this coefficient in the order such that the coefficient obtained from first multiplication will act as MSB and the coefficient obtained from last multiplication will act as LSB or least significant bit. So the equivalent binary will be 0.101 to the base of 2. And now using the same method of successive multiplication or division, we will do decimal to octal conversion. For integer part, we will use successive division. After every division, the remainder will act as a coefficient and the quotient will be divided again. And the process will be repeated until 0 quotient is obtained. Where in case of fraction, successive multiplication will be used till that you achieve 0 fraction or the desired number of iterations are achieved. For first case, look at example where we have a number 175 to the base 10 and we wish to know the equivalent octal number. This we will use successive division. In first iteration, 175 will be divided by 8, the quotient will be 21 and the remainder will be 7. Now the 21 will be again divided by 8 where the quotient will be 2 and the remainder will be 5. Now again the process will be repeated. The 2 will be divided by 8, so the quotient will be 0 and the remainder will be 2. Now all the coefficients obtained will be written in the reverse order such that 2 will be MSB and the 7 will be LSB. So the equivalent octal number will be 257 to the base 8. Second example for fraction part is we have a number 0.3125 to the base 10 and we wish to know the equivalent octal number. For this we will use successive multiplication and here we will multiply it by 8. The result will be 2.5. 2 will act as an integer or our coefficient and the 0.5 will be multiplied by 8 again and the result will be 4.0. So coefficient will be 4 and now we will write the result. Here first coefficient will act as MSB or the most significant bit and the last coefficient will act as LSB. So the result will be 0.24 to the base 8. Now we will study binary to octal conversion. We know that in octal number system we have a maximum of 8 digits which starts from 0 to 7. Now consider a binary number which is represented by 3 binary digits 1, 1 and 1. Based on their positions, if we assign weight to them and then by summing each product of weight and bit we come to know that maximum value is 7. So for representation of an octal number system, we will use 3 binary bits. So for conversion of a binary number to an octal number, we will make a group of 3 bits which will represent an octal number system. Now consider a given binary number and we are trying to find its equivalent octal number. Now for octal number, we will make a group of 3 bits. For all the binary bits which are to the right of decimal point, we will start grouping of 3 binary bits from MSB, which is first bit to the right. And here we have 2 bits 0 and 1 where 3 bits are required, so we will add an additional 0 at the end and this will complete a set of 3 binary bits and its equivalent will be 2. Now for all the bits which are to the left of decimal point, we will start making a group of 3 bits starting from the LSB. Here we have a total of 5 bits, so we will add one extra 0 to the left of the MSB. So we have 2 sets of binary bits and its equivalent can be found from octal to binary table which is given here. So the equivalent octal number will be 26.2 to the base 8. Now we have performed binary to octal conversion. Now for octal to binary conversion, simply we will write binary equivalent from the table given here corresponding to each octal number. Now we will study binary to hexadecimal conversion. We know that hexadecimal number system have a base of 16 and it represents number from 0 to F. Now if you look at given binary example in which we have a combination of 4 bits and if you assign the weight and sum up these, we will have a result of 15, which means that any hexadecimal number system can be represented by a 4 bit. So for conversion of a binary to hexadecimal, we will make a group of 4 bits and then we will assign equivalent hexadecimal value from the table. Now consider the given example and we will convert the given number into hexadecimal number system. Now we will start from all the bits which are to the right of the decimal point. Here we have 0 and 1 where we are required to make a group of 4 bits. So we will add additional 2 zeros to the right of the 1 and hence we will have a set of 4 bit which will be 0, 1, 0, 0 and its equivalent hexadecimal will be 4. Now for all the bits to the left of the decimal point, we have total of 5 bits. So we will start making a binary set of 4 bits starting from LSB. First binary set will consist of 0, 1, 1, 0 and for the second set we will add 3 additional zeros to the left of the MSB and the set will be 1, 0, 0, 0 and its hexadecimal equivalent will be 1. So the required number will be 16.4 to the base 16. And this was binary to hexadecimal conversion. Now if we wish to have hexadecimal to binary conversion, we will simply replace a hexadecimal number by its binary equivalent from the table corresponding to its position. And now we will study octal to hexadecimal conversion. In this conversion process, we will use binary as an intermediate step. Like if we are performing octal to hexadecimal conversion, first of all we will convert octal to binary, and then we will make a set of 4 bits, and then we will perform binary to hexadecimal conversion. Or if we are performing hexadecimal to octal conversion, first of all we will convert hexadecimal system to binary number system, and then we will start making a set of 3 bits, and then we will replace it with its equivalent octal number. Now consider the given example. In this we have a number 26.2 to the base 8, and we have to find its equivalent hexadecimal number system. So first of all we will write equivalent binary of every digit in the given octal number system. Like 2 will be replaced by 010, 6 will be replaced by 110, and again 2 will be replaced by 010, and decimal will be in its position. Now we have equivalent binary. Now for hexadecimal we will make a set of 4 bits. Now if you look at to the right of decimal point, we have 3 bits 010, and here we will add an additional 0, and this will complete a set of 4 bits and will result in 0100, and its equivalent hexadecimal will be 4. Now to the left of the decimal point we have 6 binary bits. So first of all we will make a set of 4 starting from LSB, which will be 0110, and its equivalent hexadecimal will be 6. Now for remaining 1 and 0 we will add additional 2 zeros to the MSB, and the binary set will become 1000, and its equivalent hexadecimal will be 1. Here the given table represents decimal numbers from 0 to 15 in its equivalent binary, equivalent octal, and equivalent hexadecimal. Thanks for watching the video. This was all about today, and stay connected for more interesting videos.